welcome to True Projects. In this video, we are going to explain about the project entitled as Lithium Ion Battery State of Health Degradation Prediction using Deep Learning Approaches. So before getting into the video, let me give you the brief description about the project. This project focuses on predicting the degradation of lithium ion battery state of health using advanced deep learning techniques by analyzing historical charge, discharge date, voltage, current, and temperature parameters. The system identifies complex nonlinear degradation patterns. Deep learning models such as LSTM and CNN improve prediction accuracy compared to traditional methods. The approach enhances battery reliability, safety, and performance in applications like electric vehicles and energy storage systems. Coming to the abstract explains that lithium ion batteries are widely used in important applications like electric vehicles and renewable energy systems, but their performance naturally declines over time due to chemical reactions and environmental conditions. To maintain safety and efficiency, it is important to accurately estimate the battery state of health, which indicates how much capacity remains compared to a new battery. The project proposes using deep learning models to analyze historical battery data such as voltage, current, temperature, and charge discharge cycles. By applying advanced neural networks like LSTM and CNN, the system can learn complex degradation patterns and time based behaviors, resulting in more accurate predictions, early detection of potential faults, and improved performance of battery management system. Coming to the existing system of estimating lithium ion battery state of health mainly depends on mathematical models, empirical formulas, and statistical techniques such as equivalent circuit models, Kalam's filtering, and regression methods. These approaches can be provide acceptable results but requires in-depth knowledge of battery chemistry and internal parameters which are often difficult to obtain in real-world applications. Additionally, traditional machine learning models like support vector machines and basic artificial neural networks are limited in their ability to capture complex nonlinear degradation patterns and long term time dependent behavior. As a result, their prediction accuracy decreases when battery operate under various environmental conditions and dynamic load patterns. Coming to the proposed system or base paper work, the proposed system uses advanced deep learning techniques to predict the state of health degradation of lithium ion batteries more accurately. It applies models such as LSTM and hybrid CNN LSTM networks to learn complex time dependent patterns for large battery datasets. The system analyzes key parameters like voltage, current, temperature, charge discharge cycles, and capacity fade while using pre processing methods like normalizations and feature extraction to improve accuracy. Compared to traditional approaches, this method provides more reliable real time predictions, reduces the need for detailed battery modeling, and adapts well to different battery types and operation conditions, making it highly suitable for modern battery management systems and electric vehicles. Coming to the dataset, the project utilizes the NASA lithium ion battery dataset provided by the Prognostic Center of Excellence, which is widely used for battery health monitoring and prognostics research. This dataset contains experimental charge discharge cycle data from batteries B0005, B0006, B0007, B0018, and B0036 collected under controlled laboratory conditions until the batteries reach end of the life. It includes detailed time series measurements such as voltage, current, temperature, cycle count, discharge capacity, and impedance, enabling analysis of capacity fade and degradation trends over time. The batteries were tested under various load and environmental conditions to stimulate realistic operational scenarios, making the dataset highly suitable for developing and evaluating deep learning models for state of health and remaining useful life prediction. Coming to the novelty or extinction or enhancement or improvement. As an extension of the base work, additional deep learning architectures such as BiLSTM and a hybrid LSTM plus GRU model were developed to further improve prediction performance. Among them, the LSTM plus GRU model achieved excellent results with an R square score of 99.7% and a very low RMSE of 0.005%, indicating highly accurate battery health prediction. The original dataset from the base research paper was also implemented, and compatible performance results were successfully reproduced to validate the approach. Additionally, to enhance transparency and trust in the model's prediction, explainable AI methods such as LIME and SHAP were applied. These techniques helps interpret the contribution and importance of each input features in the prediction process, making the model's decision-making process more understandable and reliable. Furthermore, a user-friendly web application was built using the Flask framework to allow users to input battery parameters and receive health predictions from the trained models. The interference supports predictions for different batteries, and the predicted SOH values vary according to the dataset distribution. This ensures that all predictions are purely data driven and reflect real battery behavior. Coming to the flow of the work, first, importing the packages. In this module, all required Python libraries for data processing, visualization, deep learning, evaluation metrics, and explainable AI are imported to set up the working environment. Next, exploring the dataset. In this module, the battery datasets are examined to understand their structure, features, charge discharge cycles, and overall degradation patterns. Next, data pre-processing. In this module, the .mat files are loaded, converted into pandas data frames, relevant features are extracted, and pre-processing techniques such as normalization and scaling are applied to prepare the data for model training. Next, data visualization. In this module, visual analysis such as distribution of plots and correlation metrics are generated to understand feature relationships and battery health trends. Next, split the dataset. In this module, the dataset is divided into training and testing sets using an 80:20 ratio to evaluate the model's generalization performance. Next, build the classification models. In this module, baseline models and extinction models are developed and trained to predict the battery health. Next, decentralized learning stimulation module. In this module, a decentralized learning stimulation is performed using the 1D CNN module to demonstrate distribute training across different battery datasets. Next, model comparison. In this module, graphical comparisons of all models are generated to clearly illustrate performance difference based on evaluation metrics. Next, comparison visualization module. In this module, graphical comparisons of all models are generated to clearly illustrate performance difference based on evaluation metrics. Next, model evaluation module. In this module, all models are evaluated using MAE, RMSE, MAPE, and R square score to compare their prediction accuracy and error rates. Next, comparison graphs. In this module, graphical comparisons of all models are generated to clearly illustrate performance difference based on evaluation metrics. Next, save the best trained model. In this module, the best performing trained model is saved for further use and deployment in the front-end application. Next, explainable AI visualization. In this module, Lime and Sharp techniques are applied to interpret models' prediction and analyze the importance of input feature. Coming to the front end, a web application is developed using the Flask framework with user registration and login functionality supported by an SQLite database. Users provide battery feature values through the interface, and the input is pre-processed. The trained model generates predictions, and the final battery health result is displayed on the front end. The algorithms used in the project are baseline models are 1D CNN, CNN plus LSTM, CNN plus GRU. The extension models are by LSTM and LSTM plus GRU. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consisting of Application framework Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap 4. To execute the project, first we need to open the project code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Models. These are the model files which contains the algorithm information which will be loaded into the project code during the runtime. IPYNB files. These are the Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, first, you need to copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome. So that the home page of the project should now be displayed in the browser. This is a front end built using the Flask framework. In this page, we have Home button and Get Started button. Firstly, click on Get Started button so that the Create Account form will be opened where you need to enter the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password and reconfirm your password. Then click on create an account so that all the given details are stored in signup.db and login.html will be opened where you need to access the application with the help of username and password. Click on sign in so that the user has been successfully logged in. In this page, we have predictions button, data visualizations button, notebooks button and logout button. As we are using 5 different data sets for predictions, we have 5 different prediction batteries like B0005, B0006, B0007, B0018, B0036. Now let us check the predictions for one by one. First, let us go with B005. When you click on that, the battery health prediction form will be opened where you need to enter the battery parameters to predict the state of health. So let us enter the values first, like cycle, voltage, current, temperature and capacity. All the values has been entered. Now click on predict battery health. For the given inputs, the battery health will be 98.75%, which means excellent health. Now click on predictions button and let us check for battery B0006. When you click on this, again the battery health prediction form will be opened where you need to enter the battery parameters to predict the state of health like cycle, voltage, current, temperature and capacity. The values has been entered. Now click on predict battery health. For the given inputs, the battery health will be 97.88%, which means it has the excellent health. Now click on B0007 so that the form will be opened where you need to entry the battery parameters like cycle, voltage, current, temperature, and capacity. The values has been entered. Now click on predict battery health so that the given inputs are pre-processed and the state of health value will be 99.37 percentage, which means the state of health is excellent health. Now again click on predictions. Let us predict for B0018 battery. Again the form will be open where you need to enter the parameters like cycle, voltage, current, temperature and capacity. The values has been entered. Click on predict battery health. For the given input values, the battery percentage will be 98.18 percentage, which means it is an excellent health. And now let us check the predictions for B0036 battery. Again, the form will be open where you need to enter the battery parameters like cycle, voltage, current, temperature, and capacity. All the values are being entered. Now click on predict battery health. For the given input values, the battery percentage will be of 100 percentage, which means the state of health is excellent. And now click on data visualizations so that the graphical representation of the battery predictions will be shown. Let us check one by one. First we have B0005. The battery health analysis visualizations are being opened. Let us check one by one. First we have battery B0005 SOH trend over cycles graph. This figure presents the state of health degradation trajectory of battery B0005 across charge discharge cycles. The trend illustrates the progressive capacity fade and aging behavior, helping to identify degradation phases, non-linear decay regions, and potential end of life thresholds. Next, we have Pearson correlation matrix for B0005. This matrix displays the linear correlation among key battery parameters such as voltage, current, temperature, and capacity. It assists in understanding interfeature dependencies and supports effective feature selection for SOH prediction modeling. Next, we have Pearson correlation matrix for battery B0005 after scaling. This visualization shows the correlation structure after applying data normalization technique. Scaling ensures uniform features magnified while preserving relationship, improving model stability and convergence during training. Next, we have client-wise test RMSE in decentralized learning graph. This chart compares the root mean square error across different clients in a decentralized learning setup using 1D CNN model. It evaluates distributed model performance, generalization capability, and consistency across heterogeneous data sources. Next, we have MAE graph. MAE represents the average absolute difference between predicted and actual SOH values. It provides a straightforward and interpretable measure of model accuracy. Next, we have RMSE graph. RMSE calculates the square root of mean squared prediction errors, giving higher weight to larger deviations and effectively capturing significant prediction errors. Next, we have MAPE graph. MAPE expresses prediction errors as a percentage of actual values, offering a scale-independent performance metrics that facilitates comparison across the data sets. Next, R-square score graph. The R-square score measures the proportion of variance in SOH explained by the predictive models. Higher value indicates stronger explanatory power and better model fit. Next, we have explainable AI SHAP graph. SHAP analysis provides interpretable by quantifying the contributions of each features to model prediction. It offers both global and instant level insights, enhancing transparency and trust in SOH estimation results. And now let us check with B0006 graphs. In this, first we have battery B0006 SOH trend over cycles graph. This plot illustrates the degradation tragedy of battery B0006 state of health across charge-discharge cycles. The trend highlights the progressive capacity, fading, and aging behavior of the battery. Observing this pattern helps in identifying nonlinear degradation regions, early aging onsets, and end of life indicators. Next, we have Pearson correlation matrix for B00. This matrix represents the Pearson correlation coefficient among key battery parameters such as voltage, current, temperature, capacity, and internal resistance. It reveals linear dependency between variables and helps identify strongly correlated predictors for modeling SOH estimation. Next, we have Pearson correlation matrix battery B000 after scaling graph. This visualization shows the correlation metrics after feature scaling and pre-processing. Normalization ensures that difference in parameter magnitudes do not bias model training. The matrix confirms whether relationship between features remain consistent after scaling. Next, we have client-wise test RMSE in decentralized learning graph. The graph displays the root mean square error for each client participating in decentralized learning using 1D CNN model. It highlights model generalization performance across distributed data sets and helps evaluate consistency, fairness, and robustness of decentralized framework. Next, we have MAE graph. MAE measures the average absolute difference between predicted and actual SOH values. It provides a straightforward interpretation of prediction accuracy and is less sensitive to large errors compared to RMSE. Next, we have RMSE graph. RMSE qualifies the square root of the average squared prediction errors. It penalizes large deviations more heavily than MAE, making it useful for detecting significant prediction inaccuracies. Next, we have MAP graph. MAPE expresses prediction errors as a percentage of actual values, offering an intuitive understanding of model performance relative to true SOH values. It is particularly useful for comparing performance across datasets with different scales. Next, we have R square score graph. The R square score indicates how well the model explains the variance of SOH data. A value closer to 1 suggests strong predictive capability, while lower value indicates limited explanatory power. Next, we have explainable AI SHAP graph. SHAP analysis interprets the contribution of each input features to the model predictions. It provides both global and local interpretability, helping identify the most influential battery parameters affecting SOH estimation and improving trust in the model's decision making process. Now, let us check with B0007 graphs. In this, first we have battery B0007 SOH trend over cycles graph. This figure illustrates the state of health degradation profile of B0007 over successive charge discharge cycles. The trend captures capacity, fade behavior, and aging progression, enabling identification of degradation stages, non-linear decay patterns, and potential end-of-life indicators. Next, we have Pearson correlation matrix for B0007. This matrix presents the Pearson correlation coefficients among major battery parameters such as voltage, current, temperature, and capacity. It helps reveal linear interdependencies between variables and supports informed feature selections for accurate SOH estimation. Next, we have Pearson correlation matrix for battery B0007 after scaling graph. This visualization shows the correlation structure after feature normalization. Data scaling ensures balanced feature contributions during training while preserving intrinsic relationship between parameters, enhancing model robustness. Next, we have client-wise test RMSE in decentralized learning graph. This chart compares root mean square error values across distributed clients using a 1D CNN neural network. It evaluates the decentralized model generalization capability, consistency, and robustness across heterogeneous data set. Next, we have MAE graph. MAE qualifies the average absolute difference between predicted and actual SOH values, providing an interpretable measure of overall prediction accuracy. Next, we have RMSE graph. RMSE measures the square root of the average squared prediction errors, assigning greater weights to larger deviations and effectively highlighting significant estimation inaccuracies. Next, we have MAPE graph. MAPE express prediction errors as percentage of actual values, offering a scale independent evaluation metrics useful for performance comparison. Next, we have R square score graph. The R square score indicates the proportion of variance in SOH explained by the predictive models. Higher values reflect stronger model fit and improved predictive reliability. And next we have explainable AI SHAP graph. SHAP analysis enhances model interpretability and qualifying the contribution of each input features to SOH prediction. It provides both global feature importance and instant level explanations, improving transparency and trustworthy of the models. And next, let us check with B0018 graphs. In this first we have battery B0018 SOH trend over cycles graph. This figure presents the SOH degradation trajectory of battery B0018 across charge discharge cycle. The trend highlights capacity fade progression, aging characteristics, and potential nonlinear degradation regions, enabling assessment of long term battery performance and end of life behavior. And next we have Pearson correlation matrix for battery B0018 graph. This matrix illustrates the Pearson correlation coefficient among key battery parameters such as voltage, current, temperature, and capacity. It identifies linear dependencies between features and support effective feature selections of accurate SOH prediction modeling. Next, we have Pearson correlation matrix for battery B0018 after scaling. This visualization shows the correlation structure following data normalization. Feature scaling ensures balanced magnitudes across variables while preserving interfeature relationships, thereby improving model stability and training efficiency. Next, we have client-wise test RMSE in decentralized learning graph. This chart compares root mean square error values across distributed clients using and 1D CNN. It evaluates the decentralized model generalization performance, robustness, and consistency across heterogeneous data set. Next, we have MAE graph. MAE measures the average absolute difference between predicted and actual SOH values, offering a clear and interpretable indicator of prediction accuracy. Next, RMSE graph. RMSE computates the square root of the mean squared prediction errors, placing greater emphasis on larger deviations and effectively capturing significant estimation inaccuracies. Next, we have MAPE graph. MAPE express prediction errors as percentage of actual values, providing a scale independent metric suitable for comparative performance evaluation. And next we have R squared score graph. The R squared score qualifies the proportion of variance in SOH explanation by the predictive model. Values closer to 1 indicate stronger explanatory capability and better model fit. Next, we have explainable AI SHAP graph. SHAP analysis emphasizes interpretability by quantifying each feature contributions to SOH predictions. It provides both global feature importance and local explanations, increasing transparency and trust in the model's decision making process. And now let us check with B0036 graphs. In this first we have battery B0036 SOH trend over cycles graph. This figure illustrates the state of hard degradation behavior of battery B0036 over successive charge discharge cycles. The trend captures capacity fade progression, aging dynamics, and potential nonlinear degradation phases, enabling evaluation of performance deterioration, and end of life characteristics. Next, we have Pearson correlation matrix for battery B0036 graph. This matrix presents the Pearson correlation coefficient among key battery parameters such as voltage, current, temperature, and capacity. It reveals linear interdependencies between variables and assists in selecting influential features for accurate SOH estimation. Next, we have Pearson correlation matrix for battery B0036 after scaling graph. This visualization shows the correlation structures after applying feature normalization. Scaling ensures uniform feature magnitudes while preserving interstick relationship, thereby enhancing training stability and predictive performance. Next, we have client-wise test RMSE in decentralized learning graph. This chart compares root mean square error values across different clients in decentralized learning framework using 1D CNN. It evaluates distributed model consistency, robustness, and generalization capability across heterogeneous data sets. Next, we have MAE graph. MAE quantifies the average absolute deviation between predicted and actual SOH values, providing a clear and interpretable measure of overall model accuracy. Next, we have RMSE graph. RMSE calculates the square root of mean squared prediction errors, emphasizing larger deviations and effective capturing significant prediction inaccuracies. Next, we have MAPE graph. MAPE express prediction errors as percentage of actual values, offering a scale independent performance metric suitable for comparative analysis. Next, we have R square score graph. The R square score measures the proportion of variance in SOH explained by the predictive models. Higher value indicates stronger explanatory power and better model fit. Next, we have explainable AI SHAP graph. SHAP analysis provides interpretability by quantifying the contribution of each input features to SOH prediction. It delivers both global feature importance and instant level explanations, enhancing transparency and trust in the model's decision making process. And next, click on Logger. So finally, this project successfully demonstrates that deep learning approaches can effectively predict the state of health degradation of lithium ion batteries with high accuracy. By leveraging advanced models such as LSTM, CNN, and hybrid architectures, the system captures complex nonlinear and temporal degradation patterns. The integration of explainable AI techniques further enhances transparency and trust in prediction. Overall, the proposed framework improves reliability, supports efficient battery management system, and contributes to safer and more sustainable energy storage applications. This is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.